So in proportions and ratios, another thing we want to talk about is similar triangles. They're just something that kind of automatically lends themselves to this topic because what we're really looking at is two things that are the same shape, but they're different size. And so they'll present these themselves in a lot of different ways. Hopefully my drawing is decently to scale, but what matters if two triangles are going to be the same shape is that they have the same angles. And so we can see like both of these have a right angle. If this angle and this angle are the same, it forces this other angle to be the same, right? Because it has to add up to 180. But in general, they'll usually tell you two triangles are similar. You don't have to sort that out for yourself. All right, so first intuitively, if we're just looking at this, this is a triangle where one side's 8, one side's 6. On the other triangle that's the same shape but just bigger, one side is 24. So if we can set up some relationship between these two, we can figure out how big this unknown size is. Now sometimes like this, like kind of the easiest example we can come up with, you can just see when it works out to whole numbers that it looks like this triangle is about 3 times as big, because when we compare the sides that are like each other, the one that's 8 is 24 on the other one, so it looks like they're all times 3. So you might be able to tell without doing a bunch of extra work that if this side's 6, we think this side's probably 18 units long. But let's make sure that the proportions actually work. So good news when you're setting up proportions or ratios, it doesn't matter what you put on the top or bottom. You have to do them consistently is what matters. So say if I put the big triangle side on the top, I have to do it on both sides. So totally up to you. But if we're going 24 and then there's the side we don't know, the question mark, or we could use a variable like x to stand for it. So there's 24 and the side we don't know are on both on the big triangle. Then we're saying, well, that corresponds to this side on the small triangle. So 24 and 8, right, go together, and x and 6. And so then we could solve, maybe multiply both sides by 6, multiply both sides by 8. Totally up to you, whatever you think's easier with the fractions. Or this is one of the few times I try to stay away from saying this because it confuses people on fraction multiplication, but this is what cross multiplying is literally you're just multiplying by both denominators on both sides. And what automatically happens is it cancels off one side and the other one cancels off the other side. So if you've ever seen cross multiplying, that's all it is clearing the denominators. But it's a handy little shortcut that kind of helps you out with it. All right, so this is 120 plus 24, so 144 equals 8x. And then we'll divide both sides by 8. And x equals 18. So there's exactly what we got when we just sort of looked at it intuitively and said, hey, this one's 3 times bigger, so all the corresponding sides will be 3 times bigger. All right, so you might be saying, well, then what's the point of setting up the actual ratios? Is that not all of them will work out this nicely. Having a triangle that's just 2 or 3 times as big, or this one is 1/3 the size of the other one, makes it easier to see the answer. Also, I guess it'd be a good time to show you what I mean about it doesn't matter what you put on the top or bottom as long as you do it consistently. So on that last one, we chose to put our big triangle on the top. Let's say we put the big triangle sides on the bottom. So 24 and the one that we now know, but we'll pretend we don't. The size 24 goes with the 8 and the side on the bottom goes with the 6. So these two are in proportion. It should be the same, right? If the triangle's 3 times bigger, then all the sides should end up 3 times bigger. And same thing, if we multiply, we get 8x equals 144 and divide both sides by 8, x equals 18. So that's what I mean about it doesn't matter what you put on top and bottom, you just have to get it lined up, right? If you go big triangle, bottom little triangle. All right, so then back to what we were saying about why would we even bother setting these up, is that not every similar triangle problem ends up quite as straightforward. So here's another example of a side we don't know. And this might help to look at, there's 2 triangles here, right? There's ABC, and then there's this smaller one, DBE. And so as long as these 2 lines are parallel, my drawing maybe isn't perfect, but we'll say these 2 are similar. Notice like this angle is in both triangles, so they automatically share that one in common. And so then if I tell you that like this one and this one are the same, then the other one has to be the same. And so this is one way they'll do similar triangles. It's almost like they're stretching out the inside one or shrinking down the big one. All right, so then on this one, a little bit less straightforward to tell like the sides that are corresponding to each other. On the big triangle, we have a side that's 10 long because it's 4 and 6, right? And on the short one, the corresponding side is the 6. Sometimes if people have trouble visualizing this, it doesn't hurt to like just draw two triangles, right? The one that's inside of the other one. And so label one of these. The big one is 10 and a part we don't know. And so the side on this one is x plus 4, right? From here to here is x and then another 4. And then on the smaller triangle, we have the same side as 6 and 4. So sometimes it helps to pull the picture apart like this so you can see it better. Totally up to you if it doesn't bother you to look at it this way. All right, so now we have enough stuff. We know they're similar. We can set up the ratios of the sides that are like each other. And so same thing, doesn't matter if we go big triangle on top or little. We just have to do it consistently. So let's say if we go big triangle on top, one of my big triangle sides is 10, the bottom side, right? And then my other side, the right side kind of here, the diagonal, is x plus 4. And then the little triangle, we just need to line up. So the 6 is the one that goes along with the 10, right? It's the corresponding side. And the 4 is the one that goes with the x plus 4 on the other one. And so now we have something we can solve. And so if we cross multiply, this is 10 times 4, so 40 equals 6x plus 24. Don't forget to distribute. And subtract 24 from both sides. So 20 minus 4, so 16. And then divide both sides by 6. And so there's a good example of, like the first one we did was maybe just easier to see. Hey, it's 3 times as big. This one didn't work out quite as nicely in terms of the numbers. And so we can tell the x side is 8 over 3, or if they want a decimal, what, 2.6 repeating? 2 2/3? Whatever version of the answer you want to put. So this is where being able to set up the ratios is really helpful on ones that don't work out maybe so perfectly that it's easy to do it off the top of your head.